Alright, so in the previous video I showed how you can run multiple random seeds of an optimization algorithm using MOEAFramework by passing in random seeds as command line arguments to your Java file. And you can see as a reminder again here what that looked like, parsing the input argument and then setting the random seed to that. So the next step in our workflow usually is once you do multiple seeds of your optimization run, you have a bunch of different results. You can sort all of the best known results together into a reference set, and then that comprises the best known solutions to your problem across all random seeds, potentially across multiple algorithms if you had the opportunity to run multiple algorithms. So then that becomes your baseline for measuring how well algorithms are performing. So if you're interested in measuring how well the algorithms perform relative to that reference set, you have to run the optimization again with the same random seeds, but this time you can use tools inside MOEAFramework to measure how well it's doing along the way. So I'll show you what that looks like here in the Java file. Again, this part of the file we were parsing the random seed, so that part hasn't changed. Again, you have to run, when you do the metric calculations, you have to run the exact same random seeds that you ran in the original runs, because that's how you know that you got to the reference set to begin with. Okay, so here you can see rerun optimization with metric calculations. So we're going to use this class in MOEAFramework called the instrumenter class. So before we had the executor, which runs the optimization, and we still have that below. But the instrumenter is responsible for doing the metric calculations and saving them during runtime, and then at the end of the run it will be printed out to a file. The important thing, notice here we say new instrumenter, and we're chaining all of these options together, right? There's no semicolon at the end of any of these lines. We say with reference set, new file, and then we point it to where our reference set is located. So you have to have already calculated a reference set to use this. Most of the metrics for MOEAs in general you can't calculate without a reference set. So it's important that if you want to measure performance, you need a reference set. So we tell it where the reference set is. We say we're using this problem, epsilons. With frequency is with what frequency of function evaluation do you want to record the metric values? So here, every 1,000 function evaluations, it's going to record whatever metric values I tell it to. And then you can choose which metrics you want to attach. And here they're referred to as different collectors. So we're attaching elapsed time collector, because we're going to measure elapsed time and record it. Some different metrics that we're going to use are the additive epsilon indicator and hypervolume. I think in a different video we're going to be covering what those actually mean, but those are different MOEA performance metrics. We're also going to measure the population size. So some of the algorithms have adaptive population sizing, and it's good to keep track of what the population actually is. And another metric is generational distance. So we're going to collect all of these every 1,000 function evaluations, basically. And the rest of this file looks pretty similar to before. So we have our executor, we tell it what type of problem to run, all of this boilerplate is the same, and then we say run at the end. And after the run, we use the accumulator class. We say instrumenter.getLastAccumulator. In other words, this is what has been storing all of the data during runtime. So then after the run is over, whereas before we printed out the optimal solutions, here you don't really need to do that. You already know what the optimal solutions are because you already did that, you made your reference set. Here we're interested in what the performance metrics are. So we can loop through however many iterations the accumulator recorded, and then we can print all these things out into a file. Of course, you might want to print to an actual file. Here it's printing to standard out. Either one is a valid option, of course. And you reference these things using string keys into the accumulator class. So we say accumulator.getNFE, the ith iteration of NFE, of course. And we're going to make this a tab-separated line. So NFE, tab, elapsed time, tab, and so on and so forth. And then this is system.out.println, so it'll go down to the next line. So all of the metric data will be printed out into whatever output file you specified. So you'll have a set of metrics for all 50 seeds, potentially for multiple algorithms, and that will allow you to do some statistical analysis on how well the algorithms are actually doing, and potentially to see, first of all, whether you ran enough function evaluations. If you notice that your metrics are still improving when you cut it off, maybe you want to run some more. And you can also get an idea of which algorithm potentially is best suited to your problem. Alright, that's it for this.